Okay, so last lesson we talked about tangents and normals. Now we're going to talk about two keywords, increasing and decreasing. So this here is a cubic, and this cubic here on the left is an increasing function. So what do you think it means if I said that that is an increasing function? Think about what happens to the y value. Well, the y value always goes up. In other words, at any point here, the gradient is positive, or at the very worst, it might be zero. There's no negative gradient, which explains why it's always going up. So this is an increasing function. The gradient function for any x, in other words, the gradient of this thing is always at least zero. It would be strictly increasing if it was always above zero. Small difference there. If we have a look at this function here, this might be a bit more complicated. So we could split it up into intervals. Intervals, these sections separated by dotted lines. So let's call this interval A, B, and C. So over interval A, it's increasing. So when x is less than 2, when we're to the left-hand side of 2, this is increasing. If you drew lots of tangents, they're positive. How about B? Well, it's decreasing between 2 and 4. All of these tangents have a negative gradient. And finally, it's increasing for x is greater than 4. Some examples. Show that the function x cubed plus 6x squared plus 21x plus 2 is increasing for all real values. So how can we do that? Well, there's not really enough information to judge off by drawing it. We know that a cubic could always be increasing. That kind of makes sense. Just remember, it's not always that way. Sometimes it goes backwards. But this one says it's always going up. Okay. Now, we don't need to find roots and things like that. Increasing is talking about the gradient. So let's find the gradient function. So instead of fx, let's look at f dash x. That's the gradient function for this cubic. And it's 3x squared plus 12x plus 21. I want to show that this is always positive. So show that this is increasing. So I want to show that this thing here is greater than or at worst equal to 0. Now, how can I show that a quadratic cannot give me a negative value? Well, there are many ways that we could do this one here, but completing the square was a proof that we looked at earlier. When we wanted to show that things were always positive, we completed the square with a quadratic. So what I could do is I could take a 3 out of everything, and that would leave me with x squared plus 4x plus 7. And then what I might do is complete the square on what's left here in the middle. So x plus 2 squared minus 2 squared plus 7. Okay, I think I would do it like that. If I clean this one up here, what's this bit here? So this is, because I'm going to need space for the other one. So this one here is going to be minus 4. Minus 4 plus 7 is going to be 3. And then when I apply this 3 back, I will be in a situation where I have 3x plus 2 squared. And what's that one? Plus 9. And if you remember from before, whenever you have something squared, it's at least 0. So even when it's 0, you'll still have plus 9. So this is going to be a positive expression for any value of x. Again, we discussed this one here when we did proof. Find the interval. Find the interval. So find the x values on which the function is decreasing. So when is it decreasing? Well, that's when the gradient is less than or equal to 0. So what's the gradient function? the gradient function here is going to be 3x squared plus 6x, okay, minus 9. So we want to know when this graph here is, so when the values from this are less than or equal to 0. Let's draw a sketch. Minus 9. Okay. That's what this quadratic might look like. Where does this quadratic give me values less than 0? Negative values. Well, actually, we're going back now to chapter 3. This is with quadratic inequalities. So where's the graph less than 0? Well, it's between the roots. Between the roots of this one here. Okay, so we would work out these values. I'm not going to do that one right now. I mean, you just divide them all by 3. And we can find these roots here. Let's show you some neat working of both of those. Whoops. Okay, so little conclusion there, here. Yep, so look, you see when they found the roots, they divided by 3. It came up with these ones here. So it was in between -3 and 1. This can sometimes be written like this with the square brackets to show that you're including the values. Okay. Time for you to pause the video, have a quick go at these two here. Increasing for all real values. Easiest way to do that is going to be completing the square. So what you're going to get there, you're going to get 3x squared plus 16. Yeah, there's not really much to complete here because there's no x terms. So x squared is the part that's at least 0. Okay, so 16 is the minimum value. The interval that it's decreasing, same as before. We're finding the roots from the gradient function. And then quick sketch sort of helps. 3x squared minus 135. In other words, we're saying it's between those x values there. Okay, so let's go on a little bit further. Now, we're just going to introduce turning points. So a turning point is when you have a graph. So if you have an x squared graph, the turning point is here. Okay. And what's interesting about this is it splits up the intervals that we've just talked about, because to the left-hand side, you have negative gradients, and then to the right-hand side, you have positive gradients. So, for example, here we had increasing, then decreasing, and then increasing again. So it seems to separate up the sections on this graph here. Now, this peak, we can call this peak a local maximum. It's the largest value in this area here. It might not be the largest value overall, because you might have a higher value over here, say, but it's like the peak, it's like the hill. And then you have the local minimum, and again, it's just a local minimum. But what's interesting about these points is because it's going from positive to negative, or negative to positive, at these particular points, the line must go flat. In other words, the gradient must be equal to 0. And you won't quite appreciate the usefulness of this now, but this is very important in all kinds of fields. This has many applications for things like profit maximization or optimization generally. So this is a really important idea. Find the turning points. Well, the turning points are when the gradient function is equal to 0. So I'm going to differentiate this and set it equal to 0. If I differentiate and set it equal to 0, I can solve and I can get these values here. What does that mean? It means on this cubic graph, which has no y-intercept, on this cubic graph, -9. So let's do something like this. At -9, it goes like this. and oops, and at 5, it goes like this. So you can start to find now these sections where things are turning around. So this gives me a bit more detail if I wanted to sketch a cubic, for example. So pause the video, have a quick go at these ones here. You're trying to find any stationary points. So sometimes we call them stationary points or turning points. They just mean where you have a maximum or where you have a minimum. It's where the gradient is equal to 0. Or if you prefer, f dash x is equal to 0. Pause the video, have a go. Okay, so these are just answers for this one. And it does say find coordinates. So you may have found an x value or more than one x value, but you would need to find the y values as well. Let's do one here together, x squared plus 2x. So when you differentiate it, you will get 2x plus 2. And then you're going to set it equal to 0. So x equals -1. And then, you substitute it in, okay? And you get the other value, y equals -1. So why is this important? Well, this slide we've sort of just added in to talk about why this is important a little bit more. If you were plotting these things, so imagine if you had an equation and it said the area of a triangle is given by this equation, or the distance that a toy is from the start of a track is given in this one here. This is like a mechanics question. If you draw this, you'll get a picture like this. And you can see that a particular x value, it looks like 2, gives you the maximum area from this triangle. How could I find 2 without drawing it? Well, I could differentiate this thing, set it equal to 0, and I would find out how to maximize the area of a triangle, for example. So this is an application that comes up in exam questions sometimes. How about this one here? Well, if we draw this one, it's a cubic, and what happens here, this is the distance. I'm going to put d for distance this time and call this t. This is the distance from the start. Well, the maximum is here. And the maximum, what is true at the maximum, dy dx is equal to 0. Or I should say here probably, let's make this s for displacement. Yeah, let's do displacement. So maybe this would be ds dt would be equal to 0. And you could find out that number there. Okay, so this is why it's useful. It lets you know how you can maximize things or optimize things. Let's pause the video there and come back for the next part about the second derivative.